I know that sine of alpha plus beta is equal to sine of alpha cosine of beta plus cosine of alpha sine of beta. And it does, you know, depending on which book you use, they may reverse these around at the end, but that's kind of the common way to see it written. And then cosine cosine is, oh, whoops, that's not cosine is. It's cosine squared alpha minus sine squared, oh, whoops, that's the wrong one. That's double angle identity. That's cosine of alpha, cosine of beta, minus, because that's plus, and then sine of alpha, sine of beta. Don't ask me why I remember these. Okay, so then tangent of alpha plus beta would be sine of alpha plus beta over cosine of alpha plus beta, which is going to be this divided by this. So sine of alpha cosine of beta plus cosine of alpha sine of beta over cosine of alpha cosine of beta minus sine alpha sine beta. Okay, and I actually misspoke up here because cosine of alpha plus beta only has one expression. I was thinking double angle identities. I started to prove the double angle identity for tangent, which would have been bad mixing the two. but the process is the same regardless of whether you're proving the double angle identities or the sum and difference identities. So I end up with this big mess, and that's ugly. I don't want to work with that. So can I delete this screen? Because I'm going to need more space. All right, so let's take what we just had there. We had sine of alpha cosine of beta plus cosine of alpha sine of beta over cosine of alpha cosine of beta minus sine of alpha sine of beta. And if I look carefully, I see that I can get rid of a sine of beta here and here if I was to multiply top and bottom by 1 over sine of beta. I could also get rid of cosine of beta here if I multiply by 1 over cosine of beta. But I have to be strategic in how I do this. And I know that what I want to end up with is tangent. And the way that I get tangent is by having sine in the top and cosine in the bottom. So what I'm going to do is go over here and I'm going to multiply by 1 over, I want tangent here, so I'm going to multiply by the 1 over the cosine of alpha, because sine of alpha over cosine of alpha would be tangent of alpha. And I want tangent of beta here, so I'm going to multiply by 1 over cosine of beta, because then I'd have sine of beta over cosine of beta, which is tangent of beta. But I'm choosing this multiplier very carefully. And then I have to do the same thing in the bottom, because I have to keep the expression equivalent from what it was. So whatever I do to the top, I have to do to the bottom. And what I'm going to do is multiply the top by this. So I'd have this, because this has to get distributed to each piece because this is addition. So I'd have sine of alpha cosine of beta over cosine of alpha cosine of beta, because I'm multiplying by 1 over that, plus cosine of alpha sine of beta over, I'm multiplying this in, so I have to put it over that. And then the bottom of the fraction, notice I've only addressed the top so far. Now I go to the bottom and I do the same thing, this first piece. And then multiply by cosine of alpha, cosine of beta, minus this piece multiplied by this piece. Okay, that was a lot of writing. Questions? I don't want think. I need you guys to ask questions because there's a lot of places where there could be questions here. Jaya? This one? So this is me knowing in advance. I wouldn't expect you guys to know how to come up with this, but I know that since I'm trying to write an identity for tangent, I want to end up with only tangents in my identity if at all possible. And so I see sine of alpha here. I don't want this cosine of beta, but I do want the sine of alpha in the top because tangent is sine over cosine. But in order to have tangent here, I'd have to have a cosine of alpha in the bottom. So I put cosine of alpha here. So this was something I wanted to keep, but I wanted to turn it into tangent, which means I needed to divide by cosine of alpha. This is something I wanted to keep because tangent has sine in the top, but I needed to divide by cosine of beta so that sine of beta over cosine of beta would be tangent. And then it turns out, if you look carefully, other things are going to cancel out. And then same thing in the bottom. I had to do whatever I did the top to the bottom. So hopefully I made my choices wisely and things work out in the bottom. I'm kind of at the mercy now of the identity to know whether it's going to work out. But when I come in here and look, I see there's a lot that cancels out. So cosine of beta cancels. Cosine of alpha cancels. Cosine of alpha cancels. Cosine of beta also cancels. And then I have sine of alpha over cosine of alpha, which is going to be nice. And I have sine of beta over cosine of beta, which those are not cross out symbols, those are parentheses. So then when I look at what's left, I have sine of alpha over cosine of alpha, which is tangent of alpha, plus, and I have sine of beta over cosine of beta, which is tangent of beta. And this piece all canceled, so we'd have a 0, right? There you go. So we'd have a 1. Remember, when you cancel, you're leaving a factor of 1. So there's a factor of 1 and a factor of 1. Good. And so then 1 minus, and I have tangent of alpha, and then tangent of beta. Tangent of alpha plus or minus beta will be tangent of alpha plus or minus, tangent of beta. And in the bottom, notice that this is the opposite sign there. So this will be minus plus tangent of alpha, tangent of beta. And that's multiplication. So how do you take something like this and rationalize it? Well, this is not easy. And the reason is because of this subtraction. No matter what you multiply single number wise, you're always going to end up with the root someplace. So if I multiply by root 3, it'll get distributed here and I'll still have a root 3. So the trick is to multiply by remembering how a difference of squares factors. So do you guys remember that a squared minus b squared always factors as a plus b times a minus b? Which means if I multiply two things that look like this, I will always get two perfect squares. So I'm going to use that trick here. I have subtraction here, so what should I use here? Addition. So I'll do the same thing to top and bottom. And I'll distribute now. So 1 times 1 is 1. 1 times positive root 3 is plus root 3. 1 times negative root 3 is negative root 3. And negative root 3 times root 3 is just negative root 3 squared, which is just negative 3. In the top, I have to FOIL that out. So 1 plus root 3 plus root 3 plus 3. Notice it looks very similar. The difference is in the bottom, the roots cancel out. And so here I have 4 plus 2 root 3. And here I have negative 2. This is called the conjugate. And this is a more advanced way of rationalizing. So when you have addition or subtraction with two different ugly expressions, or a nice expression and an ugly expression added and subtraction, then you use what's called the conjugate, which is you just change the operator between them. You have to do the same thing to top and bottom. And the thing is, we're not done though, because this reduces. 4 divided by negative 2 is negative 2. And 2 root 3 divided by negative 2 is negative root 3. And so that is actually, this big ugly mess is actually just this. This isn't a skill that you're going to see again.